Okay, last take on this, even if I totally mess this up, this is the last time I'm doing this. So mini unit 5B, this is our little unit, a couple topics that we're tacking onto unit 5 in this little mini unit here. This is lesson 4. This is the second part of the inverses lesson. So at the time that I'm recording this, it's actually been like a week or more since I did the first lesson. So I did go back, reference all my notes. Hopefully this is pretty seamless, but let's get into the last couple of topics and things that we need to know about inverses. So what else might we be asked to what else might we be asked to do with inverses? So last lesson we covered how to find inverses. We were switching like the x and the y coordinates. We looked at the symmetry of the graphs, how to sketch the graphs, and then we also went through how do you find an inverse function given like the original function. How do you find the one that's going to undo it? So what else might we be asked in terms of things to do with inverses? Well, often we will be asked to determine if two functions are inverses. And so the question would give you two functions, and are these inverses. Now, there are some little nuancy things that might happen with that. So you might be asked to determine it a particular way, and then depending on the format of the question, that's going to dictate what you have to do. But a lot of times the question is just, are these inverses? Okay, so you're given the two functions. So there are several ways that you might do this, okay? One of the ways is to find the inverse of one and see if it matches the other, okay? So if you know how to find inverses, then you can just pick one of the functions, go ahead, find the inverse, and then if it matches the other one, then you know that they're inverses, okay? And there's absolutely nothing wrong with determining the answer to that question that way. My upstairs neighbors. Graph both and look for the known symmetry. Okay, so we know that inverse functions are symmetric over the line y equals x, and so you could graph them both and then see if they have the right kind of symmetry. If they do, they are inverses. If they don't, they are not. Nothing wrong with that either. You could try sample numbers to see if they undo each other. And we're actually going to look at this method later in this lesson to kind of get a handle on what inverse functions actually do. Now, the drawback to that is that you'll notice that it says try sample numbers to see if they undo. Now, this can give you an idea if two functions are inverses, but because you're only taking samples, you're not verifying that it works for all of the possible values of x, okay? And so it's not ever going to be a proof. And then the last one, compose the functions to see if they undo each other. And that's more concrete, okay? It's kind of like the one right above it, try sample numbers. If you do the composition, then you know you're covering all of the possible numbers, not just your sample numbers, okay? Now, when faced with a multiple choice question, any of these methods will work. Just be aware of the limitations when checking those specific values. So if it is a multiple choice question and you have two functions and you're asked, are they inverses? And you've got your scratch paper or you have your graphing calculator, whatever you got out. However you want to come up with it is how you can come up with it. You're going to say like, yes, they are inverses, or no, they are not, or true, false, or whatever. However, if the questions are asked a specific way, then you might get pushed into one of those methods. So we want to make sure that we look at that. So some questions may take you through the composition. That is one of the common ways that we verify that things are inverses. So for our key idea in this, when inverse functions are, I'm just going to say they're composed. I don't even know if that's quite the right verbiage. When you perform composition on them, the result will be x. Okay, and what we're looking at there is like you start with like f of x, and so you start with an x, you plug like your g into your f or your f into your g, whichever way you're going to do the composition, and then you end with an x. So in other words, you do both functions and you end up right where you started. Now, you do need to check both directions to confirm. Not all the time. Okay, so if the first direction doesn't work, then you don't have to check the second. But essentially, this is what needs to be true. your composition in the first direction has to give you x. Your composition in the second direction has to give you x. Okay, so they both have to give you x. If you do the composition the first way, you get x. You do have to check the second way. If the first one does not give you x, then you don't have to worry about the second one. So if the first direction does not work, you do not need to check the second. But if it does, you do need to show that it works in both directions. And to some extent, that's a formality. That's a math formality that it has to work both ways. Okay, so we have here our these functions inverses. So we have our f of x equals 2x minus 3 and g of x equals 1/2 x plus 3 inverses. So if you try to take shortcuts with this, and I always have some students that do, they will look at this and they'll say, oh, well, this is 2 times x, and this is 2 dividing by 2. So this is multiplying by 2 over here on the left, and this is dividing by 2. Right, this is subtraction by 3, this is adding by 3. I know those are inverse operations, therefore they are inverses. And I'll have a lot of students just kind of jump to like, oh yeah, sure, they're inverses. That's not how you determine. That is like probably the worst thing you could do to try to determine if they're inverses. Now, we're going to look at an example where you can be pretty reasonably sure that it is going to work, but like, don't do that. So for composition, we would start like this. We need to look at the composition in both directions. So if you remember what I said about composition, you start with that first letter. Whatever the first letter is, that's the function. You're going to write that function down. Okay. And then you're going to take the second function, which in this case is g, and we're going to go ahead and plug that in everywhere we have an x. So we're going to have 2, and instead of 2x, we're going to have 1/2 x plus 3. And then we have the minus 3. 2 times 1/2 is 1, so that's pretty good. 2 times 3 is 6. And then 6 minus 3 is 3. And what we're going to notice is that is not x. Okay, that was x plus 3. That is not x. And so my answer to the question is no. And then if you're wondering, okay, well, what about this? We do not need to check it, okay? Because if they are inverses, then both of them are going to come out to be x. So if I get x plus 3, if I get something else, no, if it's anything other than x, like, they're not inverses, and that's all you need to do to determine that they are not inverses. Now, this one, you're probably pretty confident, like, x plus 5, x minus 5, like there's nothing even to complicate that. Like, I think they are inverses, and you would be right. But we do want to see how this looks when you're doing your composition. So we've got the fog, and then we've got our goth. Remember, those are not actual math words. And for the first direction, we're going to start with x plus 5. And we're going to take our g of x, and that's going to get plugged in there. So we're going to have x minus 5 plus 5, and minus 5 plus 5 is 0, leaving me with an x. Now, that looks very promising, but in order to actually do the proof, and this is what you would be expected to do on an open response kind of test, where you are asked to confirm using composition whether things are inverses, you would be expected to do it both ways. So for the second direction, we're going to start with x minus 5, and then we're going to plug g in, so we're going to have x plus 5 minus 5, and plus 5 minus 5 is 0, leaving me with x. And so that's what it should look like if they are inverses. Okay, if they're inverses, then you should be getting x in both directions. Now again, if the first one is not an x, you don't need to keep going. But if the first one is an x, you do want to check the other direction. I've personally never seen it not work, but that's not, but you do need to show both, okay? So let's go ahead and take a look at the next slide. So this one, our f of x equals 1 over x and g of x equals x squared inverses. Now, if you've been kind of paying attention to what inverses are and even the use of that vocabulary up until this point, you probably have a pretty good instinct of what that answer is going to be. But pause the video and work this out in your notes. So that you actually have definitive proof of what you think the answer is. All right, so we've got to see if Fogg and Goff, like we're gonna check them both. Maybe we're gonna check them both. So we're gonna start with F. F is 1 over X. And then we're going to take G and plug that in. So we'll have 1 over X squared. That is not X, so my answer is no. Okay, and you do not need to check the other direction. Now, just in case anybody did check the other direction, okay? So if you started with Goff and you started with the X squared, and then you're going to plug in the F, okay, you would end up here, okay? And that's all awesome that we ended up with the same thing, but it was like the wrong thing. So, so they are not inverses of each other. Now, practically speaking, if this is a multiple choice or a true false question, you don't have to do it this way. You could graph them. You could do f of x equals 1 over x and g of x equals x squared, and then take a look at what those graphs are and look for that symmetry. So those are some other options. Now I'm going to throw out for you a potential extra credit. So if you would like to, on your own time, so not in the middle of class, but find the inverse of f of x equals 1 over x and show all the work for it. So show all of the work for what you would find, so for finding the inverse, and submit that. I'll try to keep something open in Focus for you guys to upload that, and again, you would have to show all of the work substantiating what the inverse of 1 over x is. Okay, now we can also come to a reasonable idea if functions are inverses by testing numbers. Now this is like what we just did, except that we can, I'm looking at what's coming up next. Like what we just did, except instead of doing composition, we're actually just gonna like pick some numbers and see what happens, okay, because of what inverses do. So here's how this strategy works. You're gonna pick any number you want. I suggest like easy numbers like 0 or that capital letter A is really bothering me. Okay, sorry, that was a moment. Anyway, so pick any number. I suggest easy numbers like 0 or 1. Now, as an aside, if you're going to plug a number in here, if you see where my pointer is, for x, you are going to have to multiply it by 1/2. So it would be really nice to pick something that's easy to take 1/2 of. So if you pick like a 1, 1/2 of 1 is 0.5. Now this will still work, but it's going to give you decimals or fractions in your work. So that's another thing to just keep in mind. Like you don't always necessarily want 0 or 1. You want numbers that are going to be nice. Then you're going to take that number and plug it into f of x, and then figure out what that is. Take the result and plug it into g of x, and if you end up back at your number, then you may have inverses. Now you notice that having capital letters there, you may have inverses there. That's because you only actually know that it works for the number that you picked. And it's possible that you maybe picked like the only number that's going to come out that way on these two graphs. So you just want to be mindful of the limitations of that. We have a cat walking through. The limitations of that. So if you're going to do it this way, I would strongly recommend that you pick more than one number. Right? We have a guest with us. Say hello to everybody. He's here for the math lesson. He's not actually here for the math lesson. He's super needy, and he's just super needy all the time. Okay, so let's go over to the next slide and see what we can do with this. So thinking about this, we're gonna pick like a number. So I'm gonna pick like x is equal to 0 because I love zeros. Zeros are generally pretty easy numbers. So I'm going to pick f of 0. So we're going to take 0 and plug it in to f. And we'll go through our order of operations. 1/2 times 0 is 0. and 0 minus 3 is negative 3. Now, just for the record, what that means is that when x is equal to 0, y is equal to negative 3. Okay, now to kind of tie this in with the last lesson, if you remember in the last lesson, when we were dealing with inverses, we were switching the x and the y. And so I could ask you the question, if 0, negative 3 is a point on the graph, what has to be a point on the graph of the inverse? And I hope you remember that it would have to be negative 3, 0, that you would switch those two coordinates around. So what we do to see if that's actually going to happen is we're going to take that negative 3 and we're going to plug it in for x, okay, in the other function. And so we'll get negative 6 plus 6. G of negative 3 is 0. And oh, lo and behold, when x is 0, x is negative 3, y is 0. And so now what that would, here's the limitation on that. I actually only know that this works for x is equal to 0. If I pick a different value for x, I don't actually know for sure that this is going to happen. So this gives me a pretty good idea, like probably these are inverses. It's likely they are inverses, but I don't know for sure. So what I would strongly recommend doing, and I'm going to let you pause the video here, okay? So make sure you actually write this down because I'm going to erase all of this work. So make sure that you pause the video and write it down. Okay. And I think what I'm going to do is I'm actually going to do it 2 more times because there's a couple of things I want to point out. So looking for like another value of x, I'm going to pick x is equal to 2. Okay. And we're going to take that 2 and plug it in. So here we go. 2 times 1/2 is 1. And then 1 minus 3 is negative 2. So when x is 2, y is negative 2. So if they are inverses, then if I take that negative 2 and I make that the x for the other function, I should get a 2 out. So here we go. So we're going to go do g of negative 2 and figure this out. So 2 times negative 2 is negative 4, and negative 4 plus 6 is 2, and lo and behold, I have the switch on my ordered pairs. Now, again, this is limited, and honestly, it doesn't matter how many numbers you do, you still will only ever know that it works for those numbers. I mean, you just might be the luckiest person ever that you're picking like just all the numbers that work. However, once you've done this 2 or 3 times, if you've done it 2 or 3 times and the numbers that you're picking are all working, the chances are is that you're not actually that lucky. So probably they are inverses. So you could probably feel pretty confident at that point that that you could pick that yes, they were inverses. Now, before we leave this slide, I had mentioned on a previous slide about picking numbers that are nice, and you notice I picked 0, but I skipped over 1. Okay, I've skipped over 1 because I can tell looking at this that 1 is not going to work real well. So just suppose you did pick x is equal to 1. So we would have f of negative 1 equals 1/2 times 1 minus 3. Not f of negative 1. I don't even know why I did that. F of 1. So f of 1, 1/2 times 1 is 1/2, and 1/2 minus 3 is going to be negative 2.5. So you might have it as a mixed number, as an improper fraction. I'm going to go ahead and do it as a decimal. And so when x is 1, y is negative 2.5. And then working in a horrible way here, we're going to plug the negative 2.5 in. And so 2 times negative 2.5 plus 6. 2 times negative 2.5. Well, if you have like $2.50 and you double it, you get $5. So That'll be -5. And then -5 plus 6 is +1. And so it does work where you have -2.51, but notice how just yuckier the numbers are. So what I would recommend is pick numbers that you think are going to be nice. If you do end up picking something and you're starting to get fractions or decimals or something, maybe go back and look at it again. If you've got a fraction, picking something that is either like picking the denominator should work. Like I picked a 2, or picking a multiple of the denominator. So a 4 would work, a 6, and -2. Like those would be fine. Okay. All right. So why inverses? Like why are these a thing? Maybe I should have started the lesson that way. I don't know. Like why are inverses and inverse functions something that we do study in Algebra 2 class? So life is filled with processes that we do and we undo. Like all day long, everywhere, we're doing something and then we're undoing, and math is no exception. So what we'll do in class, if we're doing this in class, is we're going to like just generate examples of doing something and then undoing it. Now I want you to pause the video and just kind of think for a second of examples, just kind of have an idea in your head of what this would be. So examples that like have been generated before is something like sitting and standing. Okay, so you sit down and then you undo that. Maybe tying your shoes. So tie shoes and then you untie them. Okay, if we wanted to get more mathematical, we could say like we would add and then we would subtract. So we have all these like things in real life where we do and then we undo. So to give you an idea of mathematically, why is this an important thing mathematically? Okay, I have the word cell phone there. And there actually is another slide. That's what I was looking at for a second. There's my mouse. Okay, in science and engineering, we can leverage math to manipulate these processes. So I don't know that we would like leverage a whole lot of math to tie our shoes, although there is a branch of math called knot theory. I took a class in that in grad school to study knots. But I have here an example with cell phones. So most of us have a cell phone. Mine has like dinged a couple of times during the presentation. Okay, so we have a cell phone and you go to place a call. Okay, so you speak into the phone. Hi, Mom. Okay, now the way that I'm speaking is this audible voice. Okay, that like I'm speaking and my vocal cords are vibrating the air, and it's vibrating the air and it's going into a microphone, and it's sensitive to that. And what my cell phone is doing is it's changing it into an electromagnetic wave or an electromagnetic signal of some sort. Even like I'm talking in my apartment right now and it's audible and my computer microphone is picking it up and it's storing my voice digitally. Okay, so it's taking my voice and it's literally converting it into a bunch of like zeros and ones to stay in a chip. Okay, and it's converting them. My cell phone does something similar, except usually we're going to transport this with waves. Okay, travels through space. Okay, can't see it, we're not hearing it, we are not hearing all the conversations. Okay, travels through space. My mom picks up the phone on the other side because you buy a new phone. I'm going to pretend to be my mom. Okay, that's not weird at all. That phone on her side, her cell phone, has to take that signal and change it back into an audible voice. It's got to undo what my cell phone did to it. And the same would be true for like if you're watching this video, I'm sitting here, I'm talking in an audible voice. My computer is picking it up. It's storing it digitally. I'm going to process the video. I'm going to upload it to YouTube, and you are going to be able to play it back. But you definitely don't want a pile of ones and zeros. And so everything, the visual, what my camera's picking up, what my microphone is picking up, all of that that's stored digitally, your computer on your end needs to be able to convert it back. Okay, needs to be able to take it back so that on your computer screen or your cell phone or your tablet, whatever you're watching this on, you're going to get a visual image that you can see and a voice that you can hear and understand. That whole process involves math. It involves a lot of doing something and then undoing. I took an entire course in my undergrad called Signals and Systems, and that was pretty much what it was, how you have signals and send them and the math that goes into it. So obviously at the intro level in Algebra 2, we are not going to be converting signals, okay? Not doing that in this class, but I think it does give you a sense of where this math goes and how it could be built on in a future course, and how you can like appreciate the concepts and how they're used in the technology that most of us use every day. Okay, so I think that's worth ending the lesson on. All right, so as always, those of you that are my students, you know how to find me and contact me if you've got questions about this, the content, the assignment, or anything else. And hopefully you appreciated a fairly short lesson on this one.